his pants off. All right, so exercise 1. If you read through this, it says we have a jury pool for an upcoming murder trial. We have the names of 100,000 individuals in the population. So if we wanted to translate this, this is our population size, which we can denote with a capital N. Typically does not matter, but just so we have it. The percent of available jurors on the population list who are Hispanic is 40%. There's our P, our probability of success, or our real proportion. And suppose we take a random sample of 300. There's our N. So right off the bat, I have an N and a P. This is screaming at me binomial because I have those two pieces. And then I get my pat on the back. We're looking for X to be the number of Hispanics, which is about counting up successes. So if we wanted to, we could check our bins. Binary outcomes, Hispanic or not. Independent, we have a random sample. N is a fixed number, and our S, yeah, perfect. We got binomial going on here. So the next piece says, let's find our mean and standard deviation for the number of Hispanics. So this is when we'd want to go to our formula sheet or to our note card if we've written this down on our note card. Formula sheet I'll give you on the exam, and it has everything for the binomial there. So since we've already denoted that this is binomial, all we're doing is grabbing the mean and standard deviation. So no reason to waste note card space on this unless you just want to have everything in a one-stop shop. So our mean for binomial is NP, and our standard deviation is the square root of NPQ. Oops. And just so you know, that little X that's there, that's a subscript just to say that X is what we're finding the mean and standard deviation of. So don't necessarily need it. I just want you to know where it's coming from. So this is just 300 times 0.4, which means I can get rid of all of those. And then we have the square root of 300 times 0.4 times 0.6, which I actually have to do in a calculator, which is unfortunate because I don't like having to work on this stupid little calculator. So square root 300 times 0.4 times 0.6. 8.49, yes. So there's our answer choice, E. So the next question says, can we use the normal approximation? And heads up, as soon as you see a sample size this large, chances are you can, but we want us to actually check this here. This is all about that rule of thumb. Our NP and our NQ, are they greater than or equal to 10? So we can check those. We already did NP when we found our mean. We expected 120 people on that jury pool to be Hispanic. And NQ, well, technically I don't need to calculate this because I know it's going to be larger, but we expected 180, the other 180 people to not be Hispanic. And both of those are greater than or equal to 10, so yes. Oops, that's not an answer. Yes. We can use a normal approximation. We can say that X follows an approximate normal centered at 120 with a standard deviation of 8.49. That doesn't change the fact that X also follows that binomial with an N of 300 and a P of 0.4. Both of these things are true. This is going to give exact values. This is going to give approximate values. So realistically, we probably want to use the binomial, but if I ask you to use the normal approximation, you will get no points for doing the binomial distribution. Throwing this out there now. That is the most common mistake, is that students do binom CDF, even though I said use the normal approximation. So using this information, we're going to solve this question two different ways. So one says find the probability that 110 or fewer Hispanics will be selected for jury duty. So let's just do this with the binomial first. Now this is not a question Kat, get off my computers. You were driving me crazy. This is not a question I would ask you to do on the test because not everybody has the scientific calculator or the graphing calculator. So if anyone's using the formula by hand, this would be an evil question. Because if we're talking about the binomial, right, this possibilities are none up to all. So all 300 could be Hispanic or none of them could be Hispanic. And we're interested in 110 or fewer, or the probability that X is less than or equal to 110. Now this is the perfect setup for binom CDF, right? Add up starting with 0 all the way up to the value that we want. But if somebody did not have the calculator and they were using the formula, they'd have to do the formula 111 times, which is completely insane. So that's why this would not be a question on an exam, because I don't care to know. Oops, sorry, if you guys can do that. So binom, CDF, 300, 0.4, 110. Oops. Oh, that's 30 instead of 300. Let me fix that. Go back and make that a 300. 0.1312. So that's the exact value. Now, back in the day, this was something that was very hard to calculate because people used that formula. And so without technology, this became insurmountable. And that's where the normal approximation came in. So we'll use the normal approximation. Since our n is so large, we can use that mean and standard deviation we found before. We expected 120. I'll use that standard deviation of 8.49, even though it's rounded too much. It's going to piss me off. 8.4853. Sorry, it bothers me when things are rounded that much. So if we're doing a probability from a normal distribution, we would draw our curve. We would shade the region we were interested in, 110 or fewer. And we would use normal CDF. Negative E99 up to 110 with a mean of 120 and a standard deviation of 8.4853. Let's see how good this approximation is. So if we come over here and grab normal CDF, one good question students always ask here is, well, why are you doing negative E99? Isn't the least thing 0? You said that over here. And technically, yes, that's true, but you're overthinking it because the normal distribution does go to negative infinity and infinity on the two sides. So you do have to put negative E99 even if it's not a reasonable value. And same thing on the high side. If this said more than 120, we would not stop at 300, even though that's impossible to have more than 300. We would still keep going forever and ever and ever to infinity. Because what's going to happen is similar to what we saw here, whereas all that extra piece of this tail, if there is something past that limit of 0, is going to get lumped in there. So we actually do want to keep going forever and ever and ever off to that side. So, oops, normal CDF, E99 up to 110 with our mean of 120 and our standard deviation of 8.4853. All right, so on a in your note cards, you might just want to have a thing. This is all about a step 1 of finding the mean and standard deviation, step 2 of normal CDF. So we get 0.1193. So that's our probability, which is not terribly close to the 13.12%. And part of that we can fix. So if you think about the binomial, there's a big difference between saying including 110 and being less than 110. Whereas the normal, this is the exact same thing as this, right? There is no difference, but they're different for the binomial. So one way that we can sort of fix this is to think about, back to this little drawing, what these little pieces look like. So in this case, let's actually just go ahead and redo this one. Let's change this up. Oh, I have to pull out my keyboard. This was a 40% out of 300, and we're interested in less than or equal to. So this, by the way, is just going to do the same calculation, but as a simulation as opposed to something mathematical. So you can see the simulation is doing pretty dang well. But here's the issue, is that we include 110, and this actually bend things. So this is not a good drawing, drat it. But the idea here is, if I was to draw this little picture, this basically takes 110 and divides it straight in half when we want to include 110. So the next bar would happen at 111. So the way we fix this is we do what's called the normal, a continuity correction. So a continuity correction is if I want to say not this, but this, I want to include 110. What I'm going to do is actually go up to 110.5, go up right between these two bars. So that way I can say include the entire 110 bar, right? If you think of this as a bar chart. So only modification here is changing out the upper bound on that continuity, on the normal CDF to 110.5. And so just so you can see what a difference that will make, just, to basically say make sure you include that 110. Now we're at 0.1314, which is a heck of a lot closer to our exact value than it was without the continuity correction. Now, on the exam, you do not need to do a continuity correction. In fact, what I'll have is sometimes students go the wrong direction. So if you want to show off, feel free to do a continuity correction. I may offer a bonus point if you do a continuity correction in the correct direction, but you can just use whatever the heck the cutoff is and use that for direction, and you'll be perfectly fine. I'll still give you full points.